problems. And again, later, they were working also on wavelets, a very important topic. I wish all students of mathematics and physics, they become familiar with at least wavelets. Forget about finite element methods. Very, very important topic. He has a significant contributions in both the fields. I wish his talk will inspire our students here to look into that such a useful topic. See, just I don't take much time, 1 or 2 minutes, just look into his publications. Ratish Kumar and others, they have been leading people in the country on finite element, wavelets and all that. And there are topics which cannot be analyzed using conventional schemes, like say construction of a dam or construction of a house, say a bridge or some such activities. Then it is difficult to move.
Nice solution, you want to have oscillatory free solution, you want to have more economic way. So that is the reason that you are actually pervading for around the more rigorous numerical network, neural networks or artificial intelligence or machine learning approach. This is a kind of tool, but when it comes to the tool, how do you utilize this tool for solving the partial differential equation is the bottleneck, okay? So I'll be giving some of the glimpses of this work. Well, cis spectral methods also close to the Fourier and Chebyshev polynomials, basis functions. Look at this, there are many more. Yeah, back please. Yeah, if you are silent, I could able to speak. Let's be silent for another 40 minutes. Mesh-free approach. No need for discretizing the domain into grids or elements. Like, you know, all of you grid should be a structured grid. Your boundary condition should not be oscillatory, right? Should not be a gradient boundary condition. If at all there is a gradient boundary condition, if you are working on two-phase flows, you need to mismatch the boundary conditions. So there are many more drawbacks. So then people were looking at into more robust and nice free solutions, okay? That's one of the techniques, the neural network approach. Look at this, the the introduction of this physics-informed neural network. It's a kind of, you know, if you take into the one-dimensional partial differential equation, you try to frame the boundary conditions, initial conditions, and then you look at into the activation function. The activation function would be applied to the differential equation straight away, right? So when you apply to the differential equation straight away, it will work for both spatial and also for the time-dependent equations. So in fact, we are solving the two-dimensional Navier-Stokes equations with oscillatory and periodic boundary conditions, which you get applications in mechanical seals and, you know, the what we call energy savings in energy savings, especially in what we call piston rings, okay, and also some biomechanical applications, also some image processing applications, so on and so forth. Look at this. The physics-informed neural network can be a simple PD if you look at ut plus n of u lambda is equal to 0 and t is 0 to t. So what is it is? This is called UTX. If I call it as a one-dimensional latent solution, the wide range of problems can be accommodated even in the case of time-indent problems. So look at this. What we do is, there are three components in the physics-informed neural networks. Feed-forward neural network, which I was talking about the activation function, then physics-informed component, feedback mechanism. So these are the three physical components when you apply the neural network approach for simple partial differential equation. Look at this. This will have an input layer, there will be a hidden layer, there will be an output layer. Schematic representation of feed-forward neural network. You look at here, the input will have, look at this, there are three, 1, 2, 3, the small vowels which I wrote over here. When it comes kind of input what you expect. For instance, people who are using in image processing, they do use quite often log sigmoid activation function. But for physics-informed neural network, for convection-dominated problems, we use what we call a simple linear function, which I will be showing over in the upcoming slides. See that the number of neurons in the input layer is 1 or 2, depending on whether the governing PD includes a temporal component. So what kind of differential equation will you have it? Whether you have a temporal component or not, then accordingly you need to choose the vowels and hidden layers. Each layer has neurons that are connected to all the neurons in subsequent neurons. Look at this. Look at this, all of you hearing they're actually bombarding each other, right? Sometimes we see that there will be a what you call stammerage. Have you heard of stammerage? Brain stammerage. Very, very serious disease. In fact, there is a bombardment of neurons, so that's how the stammerage does occur. I mean, it's again a few seconds, so if you could able to survive in few seconds, neural networks. That is the L-1 layers, L layers. Schematic representation of working of a neuron, output from ith neuron of Lth layer, and there will be several layers. Layer 1, layer 2, layer 3, layer 4. It is something like, you know, when you apply the simple all of you know very well, what we call simple nonlinear the make a competition of each layer and see that what would be the output layer which will have a minimum error would be the best layer. Okay? Look at this. This is a typical. And what are these W's? W's are nothing but weights. Then hyperbolic tangent, that's also one of the activation function. Then we use rectified linear unit, that is maximum of 0x in the spatial component. Then we use soft plus swish. So depending on the kind of application, you do choose the activation function. Many times there would be a thumb rule. According to thumb rule, you need to choose the corresponding activation function. If you choose arbitrarily, means approximation. Look at this, another kind of automatic differentiation to compute f of x from the network, right? So how do you do the automatic derivative? Look at this ftx from the physics informed component enforcing PD structure, right? In fact, these can be applied to the, if you have only one independent variable, you can solve more easily, but then in the context of convection heat transfer, yeah, backside, keep on talking. See that either if you want to stay back and all, you have to keep quiet, right? Or else you have to leave. Either one, you should do it. Okay? So if you are applying the PDEs, you have a more than one independent variable. So you should be very careful enough. How do you apply the boundary conditions? With respect to u, and it is something like, you know, the square of that utx minus t ui whole square. Similarly, with respect to f, ftxx xi whole square. So the basic idea is MSU ensures the data variability as initial and boundary conditions. See, the more trick is that how do you handle the boundary conditions? Not just simply solving the equations, right? So it is simply when you are preparing for something, you should not do arbitrary, you know, you should have some sense of doing it. How you should be able to get the best possible accuracy, right? That is more important. Okay. So automatically calculates the exact derivatives of the output of the neural network, analyzing the sequence of elementary arithmetic operations. So that means decompose the function into a smaller functions. All of you might be doing what we call, there is an algorithm, if you are doing a design analysis of algorithm, there is an algorithm called divide and conquer algorithm, right? You do make into small sub-problems, each problem should be solvable, right? And then you do wanted to club up so that you get the optimized way of solution. That is what is called divide and conquer algorithm, very famous algorithm. So that kind of strategy we do over here. In fact, it is not actually DAE, but the strategy is similar to divide and conquer algorithm. So PyTorch uses a module called torch.autograde for automatic differentiation. So we are using what we call a Python-based module, which will have the, different libraries are available. So one of the libraries, PyTorch, which will actually encompasses the optimization of the divide and conquer algorithm in order to get the dust activation function. Well, so look at this. Once the last function is defined, PDEs with boundary condition is reformulated as an optimization problem. So that means you want to do the more optimized way so that your data connection from one vowel to another vowel, when you are transforming the number of calculations, like, arithmetic calculations, binary calculations should be less as far as possible, because every count is added to your flop count. Okay, so feed mechanism is optimization is carried out using gradient-based algorithms such as ICMAA, that is one of the strategy. Then stochastic gradient, that is one of the strategy, and back propagation, chain propagation. So the last function is typically a non-convex, right? So non-convex is, that means you will have convergence may depend on optimized choice. What kind of optimization you are choosing it? Accuracy is affected by initialization and algorithmic robustness. Look at this. The accuracy is very important. For example, okay, so this is, we wanted to have a nice and sparse gradients, right? What is a sparse gradients? Look at this, when you are handling these data points, you get into what we call a zero values, a non-zero values, right? Ultimately, you will write in terms of some transformation or some matrix. Either transformation can be converted into matrix, or matrix can be converted into transformation. The more the zeros, the easier will be the solution, right? That is what is called sparse system, right? Why? Because anything you multiply with 0, it will vanish. Anything you multiply with 0, it will vanish in the course of time. And if it becomes dense, dense means non-zeros are dominated. So when the non-zeros are dominated, every access for the data, it will be counted. So the more the count, the lesser will be the efficiency. The lesser will be the efficiency, the lesser will be the robustness, okay? Which is not advisable. So that means we'll try to get into a sparse gradients, okay? That means the gradients should be or not be far away, okay? And they should be smaller and smaller. Look at this. These are some of the gradient laws. GT is the delta WLT, MT, that is moment estimate. So all of you knowing very well, first moment, second moment, third moment, fourth moment. So the higher the moment, the better will be the accuracy, right? For example, those who are doing statistics, first moment about the 0. First moment about the 0. That is expectation of x minus 0. It is expectation of x minus 0. What is this? This is? Yeah, what is this, please? Backside student, statistics. Expectation of x minus 0. It is mean. Expectation of x minus mu whole square. That is second. Expectation of x minus mu whole cube, third moment. So the higher the moment, the better will be the accuracy. So that means, which we call it as skewness. For example, a surface is rough. How do you compute the roughness? Roughness will be computed based on the expectation of the random variable. So you choose arbitrarily some random variables called x1, x2, x3, etc. You compute expectation of x minus mu. Mu is the mean. So x minus mu square of expectation, x minus cube of expectation. So that means it should be lesser and lesser. The higher the moment, the better will be the accuracy, right? So this is one of the concept which we use it in the statistics. Okay, fine. I will not be going to too much. So look at this Broden-Fletcher algorithm. It is a quasi-Newtonian method using a Poisson gradient to approximate the inverse Hessian. All of you knowing Hessian matrix? Hessian matrix. 1, 1 by 2, 1 by 3, 1 by 4, Hessian matrix. So the idea of the Hessian matrix is denominator will remain same and the numerator will remain same, denominator keep on increasing. When the denominator keep on increasing, the whole value will become lesser and lesser. Ultimately, it will become a minutely small value. Look at this, the parameter again, it is WK plus 1. That is updated value of the weight functions. Okay. So this is a feed mechanism is optimization process continues network parameter at each iteration. So in fact, this neural network is basically a kind of iterative technique. Okay, it's an iterative technique. We don't find out any, what you call a recursive function so that the algorithm will become a recursive algorithm. It's a kind of iterative algorithm, not a recursive algorithm. Yeah, look at this. This is the basic layer of this. So you'll have a labeled data, you'll have a boundary at initial conditions, because every partial differential equation, you will have a initial or boundary conditions, right? Because these initial and boundary conditions, they do come up because of the physics informed domain of the given configuration. Okay, this is a mathematical model. I'll skip out this physics of this. Okay, we are doing a competition for the nanofluid. Okay, this is the surface velocity and stretching rate initially. So we are doing what you call a stretching sheet, and the fluid is actually a nanofluid. We wanted to compute what would be the components which would influence this stretching sheet in the single dimension case. Okay, this is a typical porous medium. You'll have a porous structure, and we wanted to find out the velocities and associated properties of this configuration, representation of computational scope through dimensional coordinates. Okay, in fact, we did it non-dimensionalization. We brought down into a dimensional equations, then we apply this PDA, a neural network approach. So this is the equations which have ultimately solved, 2 dimensionals, right? So governing boundary layer equations. So these are all convections and all those properties will have it, the what you call force equations and all those properties. So it is a convection driven case, right? So you have a continuity equation, you have a transient momentum equation, you will have a transient energy equation, and so on and so forth. And usual boundary layer approximations holds. That's the reason that you are not able to see the y momentum equation. So at the surface y is equal to 0 and it is far away. Y tends to infinity is far away from the surface. Okay, so that is u is 0, t tends to t infinity. Okay, then with these notations, these are all small notations, you do get what we call a Roseland approximation. We use it. This is the standard approximation we use in the CFD applications or in the nanofluid simulations when you do it. So this is a t for 4 is a nonlinear, which is approximated as t cube in infinity t, though whenever I write t infinity, the notation is far away from the wall. Okay, fine. So then ultimately we get what we call energy equation is in this form, dou T by dou T. There is a convection, there is a diffusion, and there is a temperature gradient. Okay, so these are all some of the physical properties for different fluids which we have taken up. Okay, then we use what we call a similarity solution in order to bring down these equations into a more compact form. So wall temperature we use it as T infinity plus T naught. T naught is the initial and Px upon 2Vf, and this is a viscosity 1 minus AT square. Okay, A is a constant. So these are all hybrid nanofluid properties which I will not be doing much. So ultimately when you do it, this PDE will be converted into a ordinary differential equation with the boundary condition. You see here, it has become third order ordinary differential equation. Okay, then we use all these dimensional quantities, and these are all very standard equations which you use it if you are doing in CFD applications, nanofluid or heat transfer. These are the some of the applications you do get quite often, and these are all I can skip over here. Skin friction is one of the output component which you need to interest in order to interpret the physics of the problem. Okay, so these are the Nusselt number. So Nusselt number is the convective heat transfer from the surface, and it will give you what would be the impact of the heat, how it is transforming from one layer to another layer, and thereby it is affecting the physics of the problem. Then you do get into what we call a domain discretization. We use it at 0 and N0, N1, N2, etc. And node structure is in this form in the linear case. The nodes are defined in such a way that I times of n infinity upon m. M is the number of layers which you are using it. Okay, so there are two types of nodes we use. One is the boundary layer nodes, one is the collocation nodes. Collocation nodes are arbitrarily fixed, so that will become a little complicated, but then the realistic problems which you do come across, they do demand the collocation nodes. So PIN is learned by minimizing the boundary layer loss at boundary nodes and the residual loss at collocation nodes. So the points are at collocated, that means there won't be any uniform spacing between any two neighbors. Okay, this is a hidden layer with the different neurons. Fine. So the activation function is tan hyperbolic S function used for hidden layer too. So as I told you, there are different, the activation functions, but depending on the kind of application which you are using it, you need to choose the activation function. For some problems, sigmoid function works very nicely. For some problems, tan hyperbolic function works very nicely. Being a practice, if you are keep on using it, you will be able to judge that which will be better in order to obtain the best accuracy. Okay, this is our residual versus automatic differentiation. We also did it, how it is helping. Automatic differentiation is PyTorch. As I told you, we use the Python library, PyTorch. Okay? So these are the residual forces for the boundary layer equation eta tends to infinity. So to compute the loss function, because for any calculation, we always interested in the loss function. What we do? Because one thumb rule is, the lesser the residue, the better would be the accuracy. This is the thumb rule, we use it in general, okay? Whether you use the, what you call, any algorithm, whether you use any software, we try to reduce the error. I mean, this is the, even by using simple calculator also, when the error becomes lesser and lesser, we get confident that the function is going to be, the evaluation is going to be a better accuracy. Same kind of fundamental to work over here. So total loss is L of W is LR plus LW, residual loss and a boundary loss. So we calculate both the residual loss and boundary loss because of the implementation of these boundary conditions. So at a different point, boundary points also in the collocation points, right? So boundary points alone will not give you a better accuracy, but you need to look at into collocation points also. So neural network weight W and biases are randomly initialized. So we use randomly initialized. Like, many people do use what you call, as your registrar was telling, students are using what you call object-oriented programming. Oops. And also students wanted to use a Python. Students also wanted to use a Java, right? See, different languages, all three are all object-oriented programming, but then each programming language has its own specialty. For example, the Java, when you are working, Java has some specialty which C++ or any object-oriented programming does not explain. That is what you call the garbage function. So garbage function is, whenever you want, you can introduce, whenever you don't want, you can leave it, and whenever you leave it, it will not access. The moment when it will not access, it will not count. The moment when it will not count, and your floating point operations per second would be lesser and lesser. That is one of the advantage. Similarly over here, in the physics-informed neural networks, this kind of facility is being available. So that's what you can initialize to 0 at any instant of time. But for example, if you are using the finite element method, but you need to identify in the beginning itself, how do you initialize, what are the local points you have to identify. Once you identify the local points, then you identify the global points. So there is a linkage. Okay. So I don't think, yeah. So it has gone. Okay. I wanted to show some simulations. Stuck up, is it? Yeah. Look at this. Look at this. Comparison of present. So we did some, what you call with the different 2009, 2011 present values. And in terms of accuracy, in terms of loss functions, in terms of activation functions, we could able to achieve a nice accuracy as compared to the previous results. So overall loss and training time also we have used. So for both spatial and also time dependent cases. Okay, so validation of skin friction and also Nusselt number. These are the two quantities which quite often we use it for simulation of these results. So we did in either cases, training time and loss function, and we plotted some of the graphs generating UPN. So there are solid lines for different nanofluids and dashed lines. And you see that when it is going to what we call the narrow, the fluids, particles, they are all bombarding each other, thereby they would be adding to the loss. So once they would be adding to the loss, then the accuracy will become better and better. So that is the interpretation from this graph. Similarly over here, you can see over here also we can see that the copper and dashed line, you see that here with the different M's. M is one of the parameter which you use it for the Nusselt number calculations. Okay, similarly this graph. So from all these graphs, see here, the lines, red lines, blue lines, they're all become closer and closer. That means the different values of when you use it, the loss function will become slower and slower, and then the values are getting deviated, either it is Nusselt number or capital M or skin friction. Yeah, these are some of the solid lines which you see here, but different values of M. In fact, we have got very good results from these two-dimensional case, and we are about to communicate this physics of fluids. That's what the thing, but then this transcript is under preparation. So what we did is we tried to calculate the skin friction number for two-dimensional convection heat transfer equations with nanofluids of aluminum and copper sulfide, and using physics informed neural networks, tan hyperbolic x as the activation function. In fact, one could try even for the log sigmoid activation function and see that what would be the error occurred in this process. Okay, these are some of the results and discussions which we adopted from this case. So these are some of the papers which we use it for the computing this, the literature. And this is a very small piece of work, how you can use for CFD applications, the approach of neural networks, not rather than using usual approach like finite difference, finite element and all. This will have its own speciality because it will have mean square error computation, and how the neural networks can be used for CFD applications. Ultimately, you want to solve the partial differential equations with initial and boundary conditions. So the students or the researchers who are starting the computational work, they can go ahead with this neural network approach. Only thing is, you should be familiar about a programming language which I use what we call Python. Okay? You can use even MATLAB also, you can use it, but you need to read more and more how the software can be used. Right? Okay, so this is a small talk which I brought it for especially for the beginners who wants to use a neural network approach for solving the CFD applications. Okay? Yeah, so I made it very short. I exceeded my time? Oh? Okay, I am within the time. So now I will request all the audience backside who are sitting to question some of the, you should ask some questions. You might not have understood fully, but then it may be vague, it doesn't matter. So should ask. Especially those students who are doing a machine learning course in MSc. Yes, please. Okay. See that the stochastic PD is, in fact, it's a much more difficulty than what you used it. The moment when you are talking about stochastic, there is a randomness. So the randomness means it is abrupt. So people have been using in turbulence. So there you get what you call a stochastic turbulence. I mean, there is no prediction, these unpredicted variables. So people have been using it in different contexts. So stochastic PD can be solved in this using.
Sir, I have one question. So you spoke about the weights, right?
Weights, right. Okay, so it's a weights are nothing but, all of you knowing very well the Gaussian quadrature, no? Gaussian quadrature knows? How many of you knowing? Many more. Gaussian quadrature. So you want to approximate the area under the given curve where the points are not equally spaced. So you use 2-point Gaussian quadrature, 3-point Gaussian quadrature, 4-point Gaussian quadrature. The higher the points, the better will be the solution. But then solving the higher equation is very difficult. Like, for example, you can ask a question, why do you want to solve only second order PD? Why can't it be third order, fourth order? Right? So, the second order itself is very minutely small changes. If you go to the higher order, you will not be able to solve it. Because it's good. I mean, higher order, the better. Because your work can be done by 10 people. If you allot to 100, it is easy. But what they will do 100 people? So same thing with higher order differential equation. Okay, so it can be done, but then see that not just solving now, what is the output you are going to get it? That is also important. So small changes, again you want to very small changes, so when you put in the denominator it will blow up. So you have to be very careful. So to what extent you have to be taken care. Yeah. I want from MSc students, no? Yeah, Professor Kulkarni, yes. Okay. So Professor Kulkarni is, how do you ensure the iteration? What is the stopping criteria?
My question is, how do you ensure that the fitting doesn't exceed or go out of radius?
Okay. So, yeah, his question is, how do you control the iterations? I mean, the iteration techniques, and there are a number of ways of doing it. The one way what we do is, there is a Courant-Fisher-Levy condition, especially these grid techniques. So the condition what it says is, you take care of the spacing along the x direction, spacing in the y direction. You try to do a delta x, delta y, where small value multiplied with again a small value which will be very smaller value. And when you are putting into the iteration delta x, delta y, so it should become smaller and smaller. But then we remember that sometimes it will blow up. So for that there is a what you call different conditions are being available. One of the condition is Courant-Fisher-Levy condition. That's for the stability of the schemes. That's what entirely, what he pertained to ask. How do you control that? That's what probably? Yeah.
This PyTorch will take care of that?
Yeah, PyTorch will take care of that, as he told. Because that is already being available. PyTorch is nothing but a library. Python library. So library you should understand, but everything is available. But before understanding, you should know that how it should be used. Yeah. Backside students, no? See that if you are not asking a question, I will not going from here. Yes, you want to leave me or you want to stay back? Tell me quickly.
Sir,
Yeah. Yes, Janardhan.
using artificial neural network, so we can calculate the Nusselt number or using our own numerical methods also like Gaussian integration or Newton cotes integration, so we can get the value. So but some people are calculating the Nusselt number through this ANN. So what is the advantage of that ANN? I think compared with the numerical methods. That is what.
Okay. So this is one of the advantages when you are solving the typical PDEs, like just not non-linearity, not because of convection, there may be some oscillatory boundary conditions, where the boundary conditions are typical when you apply it, and simply calculating the Nusselt number without using the ANN may become very, robust, but may not be able to fetch the solution which you wanted. So to get the more and more accuracy, this is one of the way. Like for example, finite difference also I can get a best solution.
Yes.
But then it has got its own limitations. Okay. Similarly, this artificial neural networks also has got its robustness, and this is one of the way that how you could able to achieve with minimum flop count. That's the one technique.
And also, sir, can we apply the ANN to the governing differential equations?
Yeah, directly you can apply the governing equation. Directly you can apply with it. So this I did it because to elaborate the, for beginners, so I did it in different way.
But
otherwise you can apply
even
directly.
in the literature, I
Yeah,
checked,
even in the literature you directly can apply.
many people not applied directly ANN.
Yeah,
but
because
they are applying the numerical methods, and then while calculating the.
Yeah, because you want to include many more parameters, no? You want to have a oscillatory boundary conditions, you want to have a sparse matrices.
Might be difficult.
You are different. It's a difficult. So easiest way is to try to do all those numerical procedures, then use at the end of the neural network.
I got
this. Yeah, please backside. Yeah. Yeah, please. Yeah. Huh. Nice. Yeah. Actually, her question is, basically neural network artificial intelligence you are using because you are handling the huge data. You have got so much money, you want to count with hands, you want to have a machine, right? Because you have got so much money, you will not be able to count. You don't want to count. You can count, but you don't want to count. You will procure a machine. Similarly, in the realistic situation, you are handling the huge data. So in order to handle the huge data, you want to have some training function. It will train you. Train means it will how do you get the best accuracy and best calculation. That's the basic idea we did. Okay? So whole problem comes because you have a huge data. For example, all of you are there, right? And you want to listen to the professor talk. You also wanted to see your WhatsApp. You also wanted to some messages. Multitasking, you want to do it. Is it not? You wanted to talk. Who told you to do multitasking? Who told you? And it is the need of the day. You can't wait till the lecture is over. You keep on messaging and all. You are sometimes noting down and you are chit-chatting this thing. I mean, it's the need of the day. So similarly, it is the need of the day. So you have to have such kind of a huge data. Okay? Fine. Yeah. Anything from boys? I gave very elementary talk, not the very hi-fi, right?
network.
Got it? Anything? Huh? I'm not going to conduct any exam. Okay, fine. So already we are late, probably. Yeah.
ಅವರಿಗೆ ಬ್ಲೂಟೂತ್ ಒಂದು ಸರ್ ಕೊಡಬೇಕು ಇವು ಬರ್ತಾ ಇಲ್ಲ ಕಣೋ ನೆಟ್ವರ್ಕ್
So I think we are already 2:20.
ಸರಿ ನೋಡೋಣ ಅದು ಬರ್ತಾ ಇಲ್ಲ
IIT people, they are going in a galloping way. I thought he's still there at finite element, wavelets. This is neural network, soft computing. It has more versatile features where we can incorporate many other aspects. I don't know. You should have highlighted about that. I didn't know about abstraction and all that. Okay, but a very good talk. I wish our students working in fuzzy topology, fuzzy sets,
You know, all of you know him,
they will
Professor
be
Muzirke, sir?
benefited.
He's one of the oldest teacher retired, and he happened to be my PhD Viva examination in 2000 in IIT Kanpur. So I have got 25 years of association with him.
You see, very important. Because we are in the field,
2001.
we know its importance.
24 years.
There is a
So I
one
graduated
topic,
in 2001.
soft computing. All this greedy algorithm, fuzzy sets, so wavelets, so all these, they go together. You see, all the important features of those topics are put into that. That is the advantage. And again, he was mentioning about, I don't know how many students have seen. He started with compressible fluid flows.
Correct.
And it is a tough job. To deal with compressible conventional topics, you have to struggle, converting it into similarity transformation and all that. But he was able to do it in a much comfortable way. That is the importance of good tools or good methods. We thank Professor Rao for presenting the
Thank you for one and a half
important
for, although it's a
topic
lunch
to our
time for you,
students.
but
I wish
I was
those who are
here.
interested, you try to be in
Many of
touch
you
with
must be
him.
cursing also, I believe.
Thank you very much.
Thank you for changing the session.
So again, good afternoon to everyone. Yeah, so our talk would be Professor Dr. Kiran Kulakarni, a senior principal scientist from National Chemical Laboratory. It's one of the premier laboratory in India. It is situated in Pune and it is under the CSIR, Council of Scientific and Industrial Research. So he works on many areas: structural biology, X-ray, crystallography, computational biology, right? Many more versatile areas he works. And he is basically a physics graduate from your university, right? He did his MSc in 1997-96. So 97-99. So he is your physics graduate. So he is your alumnus. Okay? So, and then he did his BSc from Hubli and PhD from Indian Institute of Science, Bangalore. You know, it's one of the dream institution in India, especially for biology, chemistry, and many more. So they are very crazy, you know, those who wanted to do PhD in India, chemistry or biology, molecular biology, things like that. It's one of the dream institution, okay? So he has got the alumnus of ISC Bangalore also. Now I request Professor Kulkarni, probably he would be sticking to his time, around 30 minutes, because I know that all of you are very hungry, especially I am also very hungry. So, because everything I should not put on you. So he would be taking 30 minutes. So by 3 o'clock we will be out of this room. I will ensure. Okay? Please.
Yeah. So now, let me thank Rao for kind introduction, and I also want to extend my thanks to Professor Shiraz. Okay. Am I audible now? I mean, it's quite echoing. I know that all of you are hungry, and when stomach is empty, brain makes a lot of noise. So I just ask you to refrain from making such noise, because I'm not going to take much time. And the thing is, I'm also hungry, so I may not have that kind of force in my voice like the previous speaker had. He gave you a blast of mathematics, although he claims that it was a very preliminary work. I am not going to talk much mathematics because I am not a mathematician, okay? I am the beneficiary of mathematics. I have been benefited out of the techniques what you people have developed, and I am going to tell how I have adopted mathematical techniques in my research, in understanding something about protein structures, in understanding something about cancer. Okay, and I presume that most of you know about proteins, but you know, for the sake of completeness, I am going to give you a crash course on protein structures. Those who find my talk, especially elementary slides, as kind of rudimentary information, my apologies to them. And trust me, I'm going to next 30 minutes, I'm going to entertain you. And if I fail to entertain you, it's not your problem, it's my problem. Okay, great. Okay. So. Oh, some technical glitch, you know, including system. System is also hungry. So, okay. Oh, okay. My apologies.
Getting connected.
It's getting, yes, yes. Coming back to life.
It's connected.
Yeah, sure. Yeah, it will come. Oh gosh.
Connected. ಇನ್ನೊಂದ್ಸರಿ ಕನೆಕ್ಟ್ ಆಗ್ತದೆ ಹಂಗೆ ಹೋಗ್ತದೆ ಅಲ್ಲಿ ಲೂಸ್ ಕನೆಕ್ಷನ್ ಐತೆ ಇನ್ಪುಟ್ ಹತ್ರ ಚೆಕ್ ಮಾಡಿ ಅಲ್ಲಿ ಇನ್ಪುಟ್ ಹತ್ರ ಬ್ಲೂ ಕಲರ್ ಕೇಬಲ್ ಐತೆ ನೋಡು and disconnected.
Hopefully, there's some loose connection. Otherwise, okay, just to engage you, somebody asked me during coffee time, what is my area of expertise? So I told them that I did BSc Electronics, MSc Solid State Physics, PhD in Biology, postdoc in Cancer Research. I also hold a fellowship in oncology. So I'm a kind of a partial doctor. So now you can guess what I will going to speak. I mean, what is my level of understanding of mathematics? I will try to do justification to the title of the conference, and hopefully I will going to entertain you for next 30 minutes, if everything goes well. Oh,
ಇಲ್ಲ ಸರ್ ಬಂದು
okay. Yeah, thank you. No problem. Yeah, it happens. So technical glitches are always, they are not in anybody's control. Okay, just a brief introduction. What we are up to. So what we want to understand is that you see here something called as biosphere. Okay, we have a biosphere, and biosphere is made up of ecosystem. Ecosystem is made up of communities. Communities made up of population. Population is made up of organisms. Organisms are made up of organ systems. Organ systems have organs. Organs are made up of tissues, and tissues have cells and molecules. Basically, we want to understand this entire spectrum in terms of these molecules. Trust me, it is extremely complicated task. Why it is complicated? Look at the size we encounter. So I'm sure you people know 1 nanometer is 10 to the minus 10 meters, and we have a human being which is of the order of 1. So you have to reduce the order of magnitude, several orders of magnitude, to reach the molecules. How can we explain this entity in terms of these molecules? So the complexity doesn't stop with the size. Look at this is, I intentionally put this slide. This shows the kind of proteins which are present in our gut, in our tummy, nam hotteli, and these molecules interact to digest the food. Can you gauge what is the complexity? I mean, it's extremely complex. So when we have such complexity in terms of size as well as interaction, you have to invoke different mathematical tools to understand them. And how can you understand them? And there's a standard technique, something called as reductionist model. I'm sure you know what is reductionist model. Suppose an alien comes to Earth and he or she doesn't know how a car functions. Alien doesn't mean Amir Khan, somebody else, or maybe, okay? And that person doesn't know how a car functions. Then you can dismantle the car into its constituent elements and study them individually. That will give you a glimpse of how each component work to make a car. So that's perfectly fine in biology. So what we do is that we study the molecules by segregating them from the cells. Okay, and for example, our cell is made up of these macromolecules. We have proteins, we have DNA, we have sugars, we have blah, blah, blah. So what we do is we just, remove the ingredients, isolate them, and study them one by one. So amongst these proteins are the workhorse of the cell. Workhorse means they do a lot of, I mean, you name any biological process, you will find one or more than one protein involved. I'm seeing you because of protein called rhodopsin. I'm breathing because of protein called hemoglobin. I'm moving my hand because of protein called, collagen. And there are multiple proteins. At least one or multiple proteins involved in all biological processes. So if you want to understand biology, or if you want to understand life, you need to see, or you need to understand how these proteins function. Okay, now coming to the crash course. What are proteins made up of? Proteins are the linear polymers. They are the linear necklace of amino acids. There are 20 amino acids, and just bear with me for 1 minute, and this 1 minute video will show you how proteins are formed. You see, there are 2 amino acids, they come together, they form a peptide bond, and these peptide bonds, they grow together, and it forms a huge linear polymer. I hope I can speed up this video, and this polymer folds into local structures, which we call them as secondary structures, and then these secondary structures fold into what is known as a globular protein. Just bear with me for 20 seconds. So these are the local structures which form, and these local structures have this kind of shape. This is a representation, and then such local structures come together to form what is known as a tertiary structure, and these structures assemble to form what is known as a quaternary structure. I mean, this much of crash course is required to understand my further talk. Okay, so these are 2 types of structures, what we call beta sheets and these things, and they come together to form what is known as tertiary structure. Just 10 minutes. I should have fast forwarded this video, but okay, this is coming to an end, maybe 5 seconds. Okay, tertiary structures come together to form what is known as quaternary structure. So if I just look at proteins, in terms of atoms, these are the atoms, but for our understanding, what we do is we represent them like lines, or in sometimes like these cartoons. These are called as cartoon structures. They help us to understand how protein function, okay? Now, what are we interested in? We are interested in understanding how cells move. Why? Cell migration is an essential process in biological events. Like, you might have seen, if you have a scratch on your skin, the cells from the opposite side, they crawl and close the wound. Okay, and when fertilized cells, they move in different directions to form organs and organism. This is a classic video taken by David Rees. I will forward this one. This is our white blood cell, the one which is moving, and the black one is the bacteria. It's actual real-time movie. The bacteria is chasing, the white blood cell is chasing the bacteria, and it will going to eat up. So it is involved in immune system. So what we are interested in, we want to know how cancer cells move. Why? So there is a process called as metastasis, where tumor cells from primary tumor location, they enter bloodstream and cause tumor growth elsewhere. So if you can stop this one, basically you can cure cancer. So we want to understand how these cancer cells move. Okay, I told you just now that if there is a biological process, you need to find out what are the proteins involved in them. And this happened some time back. Look at you appreciate the complexity. How I showed you a video where white blood cell was moving. These are the proteins which crosstalk with each other. They have their own social, networking system, like, they have Facebook and whatever you call. So they exchange information to exert that kind of, migration. So we wanted to understand, the first step is we have to find out how the information propagates, how the system, understands that I have to move, how the cell knows that, okay, I have to move, I'm here, I have to go in this direction, I have to stop, I have to go in this direction, change direction, all these things. So it has to be spatio-temporally regulated. So it started with a guy called Professor Alan Hall. What he did is he purified some proteins. He was in Switzerland, ETH Zurich, and he injected them into the cells. So the cells were earlier like this, and when he injected the proteins using some micro syringes, they showed some kind of patterns. These patterns are seen when the cells move, especially tumor cells move. So, okay, so what is the conclusion? Conclusion is that these are proteins which are essential for cell migration. If cell has to move, these proteins have to function. How do these protein function? Well, they behave like biological switches. Okay, there is a small molecule called GTP, guanine triphosphate. When they are bound to GTP, they are on. They are switches, right? And when they are bound to GDP, they are off. So they shuttle between on and off state. When they are on, they act on many other proteins and exert cell migration. Basically, they make the cells to move once they are bound to GTP. Okay, so there is a switching happening. So can we stop this switching? Because we want to stop cell migration, right? Okay, so to understand this one, we need to know how exactly these proteins function. So this is the example of a protein called KRAS. I would like to highlight your attention here, just see that there are 2 segments in this protein, which we call switch 1 and switch 2. And what these do is that they basically, they change their conformation. So when it is bound to GTP, it is like this. When it is bound to GDP, it is like this. So this is called as loaded switching mechanism. You can see that this particular segments are moving. Okay, so to understand switching, I need to know how do they move these segments. So what is the internal migration? Okay, what happens, why we are interested? Because these cells, they exert lot of different kinds of migration, and in more than 65% of aggressive cancers, these are mutated. Means they lose their switching action. So if I can understand how they switch, then I can probably develop a drug which can either stop them or it can modulate their function so that I can modulate cell migration. Okay, so why I gave such an elaborate introduction? Because our ultimate goal is to cure cancer. Okay, I mean that's what we say to funding agency, but we generally mean that one. Okay, so we have to address these all types of cancers in which these switches they fail to function. Okay, now see, to apply any mathematical technique, the first step is definition of the problem. You have to define the problem thoroughly. There should not be any loopholes. So if you have a correct definition of the problem, then you can always find a solution for that. I mean, there are so many tools available. Okay, the problem is even more complex. I told you that there are two segments which shuttle between on and off state. They are like this, they move. Okay, but subsequently some other members, some cousin brothers of this GTPases were, I mean, we got to know their structure and look at it. Some of them have dramatic change, huge change. Some of them have no change at all. Look at them, they are almost same. There are two states which are shown here with different colors. You can see that there are, some of them have huge dramatic change. Some between, some segments which are in between the proteins, they come and they occupy. So, I mean, how can you quantify them? How can I know? By just knowing the structure of the protein, can I tell whether is it in on state or off state? And the problem gets compounded when you see that when there is a mutation in the protein doesn't tell us how it's moving. And if it doesn't tell us how it's moving, then we don't know the switching state of the protein. So how can we understand the switching mechanism? So can we apply a mathematical technique to understand the switching mechanism of GTPases? That is the final definition of the problem. Okay. Now what tools are there, mathematical tools? There are many signal processing tools, but to achieve that one, I have to convert these structures into signal. That's the first thing. Okay, what is a signal? Okay, I mean this is I made this video using AI. So you can see that the boy is standing in front of the shore, in a shore, and there are waves generated by the sea, and there are birds which are tweeting, and there is a wind. So all this particular site is full of signals. Why I showed this animation? Because there are two types of signals. One is temporal signals, means which change in time, and the other one is spatial signals, which change in space. So here what is happening is that there is a conformation change, means the protein atoms are moving. There is a spatial change. So we have to convert this into a signal. So then, just 1 minute. So how can I convert it into a signal? So what I did is, we took the atoms and we asked who are its nearest neighbor. Why I'm asking this question? Because if the neighbors change, means I know that that particular atom is moving. So this is called as residual contact order. I mean it's a very standard thing. It says that this is the distance between ith residue and dth residue, provided they are interacting, means they are within the 3 angstrom range. Why 3 angstrom, why not 10 angstrom? I mean, that is the debate. I may address it later. So if you convert this one, what we have is these are residue numbers, and we have contact order, residue contact order. So basically, what I have done is dimensionality reduction. From a 3-dimensional structure, I got a 2D plot. So I have reduced a. Okay, this is not my problem. Okay, now once we have this signal, we can. Once we have the signal, we can always try to get pattern. And one thing is, all of you know Fourier transform. Fourier transform is basically, it is, it's just mapping the components into its fundamental frequencies, what you call, it's again, you're just, you're defining the orthogonal basis system, and you're just calculating the contributions of that one. So, but the problem with Fourier transform is that it loses the time information. You can see that there is a signal which up to 2 seconds it has a frequency of say 5 kilohertz, and then from 2 to rest the frequency is changing. So if I take Fourier transform, I get a peak like this, which shows that what are the components available. If I reverse the signal, from here you see that it started from 0, and again up to 2 it has a higher frequency components, and after 2 seconds the frequency component changes. But if you take Fourier transform, it's exactly same. So if I take Fourier transform, I lose this time information. So that's a problem. But this problem can be circumvented using wavelet transforms. I mean, I'm sure most of you have studied wavelets. They are basically, you take a mother wavelet and you just scan it throughout the signal, and then you will gain both spatial values as well as frequency values together. I mean, you won't lose. And it is very much adopted in our routine medical diagnostic like ECG. This is an ECG picture. This ECG picture you obtain after converting the actual signal into wavelet transform. So now you look at it. So this is the Fourier transform, but if you take wavelet transform, you can see that this is a time component and the frequency component, arbitrary value. You can see that the frequency component here it is changing, but if you take the ulta reverse order, you can see that the frequency component is decreasing. So if you can by using wavelet transform, you can restore the temporal information. So now we have a signal and we calculated wavelet transform of the signal. Now, this is called as mother wavelet. There are several mother wavelets available. I saw in the abstract book that there are several talks on wavelet, and somebody will going to explain to you how do you choose the basis vector and what kind of mother wavelet you have to choose, and what is this is called as scaling factor, and what is the sample frequency, and all these things you will going to hear from someone else, because already you are hungry, I am also hungry, so let us take. So this is how the mother wavelet looks, and what we have done is we have taken this one and we have scanned it throughout the signal, and then what you get is this. So this is this has three values. I mean, you have x-axis, y-axis, and there is a color component z. So if you take our signal and do this kind of transformation, I told you that what is the right choice, what should be the scaling factor, what should be the sampling factor, and I told you what should be the number of, what should be the distance cutoff. So you can see that as, we have just taken this for different proteins, and we have calculated for different distances, we have used different scaling factors and all, and we have calculated the Fourier transform to see which Fourier transform gives us more information, means where the information is not lost. So I can just go on and explain this to you, but in the interest of time, I'm just moving ahead. So what happens is that we have two states. This is the protein bound to GTP, and this is the protein bound to GDP. I showed you that they change conformation. I convert them into signal, and I take wavelet transform. I follow the same protocol here, and then I calculate what is known as cross wavelet transform. I mean, I calculate the, it's just, if you have two functions, you can just, you can overlap, you can calculate the overlap function, or you can calculate wavelet cross correlation amplitudes. And once you do, what you get is something of this kind. Now, as I mentioned, you see it has the x-axis, which is, you can say it's a residue number, and this is an arbitrary unit of change. And this, there is a phase component, because the phase component comes when you do cross correlation. And if you plot this phase component, which are weighted by the change is given by the color, and when you calculate this thing, you will get three vectors, one corresponding to the switch 1, switch 2, and the loop region. And when we plotted these values, we could see this one. See, this is the CDC42, one of the members between GTP and GDP. This is a KRAS, and this is a protein which has a mutation. In cancer, this particular mutation is observed. So what happens? So we can see that you see here we have different distribution of vectors, and the vectors have different angles as well as amplitude. So if we calculate their what I should say, their projection on the y-axis. The projection on the y-axis we can capture both their orientation as well as the extent of the vector. So if we calculate the projection of these vectors on y-axis, we get these values. And you can clearly see that switch 1 and switch 2 regions have almost same value for normal protein. Although they show different the amount of motion is different in all of them. But in cancerous mutations, you can see that there is a huge change in switch 1 conformation. The values are attributed to switch 1 region. So this is, what we have achieved is that we have achieved something. We have deciphered the signal, which cannot be deciphered just by visual inspection. If you have two structures, you can just superpose them. You cannot understand that there's a change, and that change is responsible for the switching action. So people will ask, okay, these are the static pictures. What happens if you have a huge sampling space? There has to be a huge confirmation space available. So for that, what we did is we just performed molecular dynamic simulations, and you can see that once we have molecular dynamic simulations, instead of one vector, we have a distribution of vectors, and accordingly we have distribution of projection values. And when we plot, we can see that there is a fantastic correlation between switch 1 and switch 2 region. And you can clearly see that in cancerous cases, the correlation breaks down. So this is a fantastic illustration that by performing wavelet analysis on structures, you can decipher the hidden information, which we call it as latent information present in this one. So this particular slide was meant to satisfy the reviewers. They say that your correlation values are very low. Then how are you going to prove? But what we figured out is that there is no linear correlation. Instead, there is a non-linear correlation, and which you can figure out from this MCG values, and they are well within the limit. So this is the last slide. So I thank my students Zinia Motiwala and Anand Sugirti who performed, and we are thankful for Dr. Durba Sen Gupta for her inputs as a collaborator. Thank you.
So thanks a lot to Professor Kulakarni for sticking to his time. Any other one or two questions quickly? Yes, please.
When I hear most of the biology talks, they used to talk about proteins. I am from mathematics background. We have other molecules also, carbohydrates, lipids. Why we should be more interested in proteins?
My third slide, proteins are the workhorse of the cell. Without proteins, no biological process can take place. Hence, almost all drugs, 90% of the drugs available in the market, they target proteins. So either you stop them, or you activate them, or you deactivate them. That's why everybody is interested in proteins, because proteins are the workhorse of the cell.
Yeah, so I think
Yes, sir, it's very interesting. Because you were talking about the drugs and all, in your laboratory, whether you used the supercritical properties for supercritical fluids?
No.
So
I'm not a fluid dynamics person. What we do is we get the structure of the protein, and we have fantastic chemists in our.
So you are not working in drug delivery or drug design?
I work on drug design.
That's
drug
what.
Design doesn't require any supercriticality or something.
Yeah, no, if we apply the supercritical properties.
It's not required. Basically, what we do is we design a small molecule which either inhibits the protein or it activates the protein. So we look at the active site of the protein. In this case, the switch 1 and switch 2 regions. And we try to arrest their motion by designing small molecules. So other than that, it's more of what I should say, it's approximation, because you have thousands and thousands of proteins available. So there may be some cross-reactivity and all. So it's a complex phenomenon, and we solve this complex phenomenon by using approximation methods.
Okay. No. Yeah, because I have submitted recently to the ANRF proposal supercritical fluids, I think, for the better drug delivery, better drug design.
So probably yours is for formulation.
Yes, yes.
Yeah, that's fine. Yeah.
Yeah.
But you cannot, that's why actual inspection cannot give you that.
No, he wants that, what is the software, any other software?
It's Spywall. You can use it.
That's what, no? Yeah, Professor Buzirki last.
Protein, analysis of protein structure, beautiful analysis tool, wavelets. In our experience, we find little beyond that. That is, frames have a lot of advantages over wavelets. Which wavelets they are used here? Which wavelets?
Which wavelets they are used?
Tupachi
we didn't
wavelets,
use that
Bayer
wavelets.
wavelets, any idea?
We use
Packages, they will be giving information. They have limitations. They have limitations.
we tried with
In image processing or communication, you see, if you add some extra data, you are through. Or if you remove some,
No, that's why
you are through. And if you have huge data, stability comes. So for all that, people have gone little beyond. Frames,
more like we use
frames, frames.
Morlet. I mean, this was the question asked by the reviewer.
No, what
and then we addressed it by optimizing the all parameters.
So thanks to Dr. Kulakarni for nice talk. Okay, thanks a lot. So now all of us, now next course of action, Professor C.L. Shetty sir will be announcing, we'll be going for, what is the next course of action for them? Lunch.
Thank you, sir, for chairing the session. Now it's time for a lunch break. I request everyone to have food and gather here at 4 o'clock.
So let us move for the lunch, and then only lunch cut down into 30 minutes. Immediately we have to rush back here. Two venues are there, one for the students, another venue for the teachers, for the dining. So please move there. At the end for the teachers, in between for the students.